Hello everyone, welcome back to our course series of Python for data science. In this video we will discuss about Python library for number, called as NumPY. In this video we will discuss about the what number library is and also how can we use number libraries to perform numerical operations on it. The NumPY is the short form of numerical Python. It provides a well-organized interface to store and perform mathematical operation on the dense data. In some way the NumPY arrays are like Python's built-in list data type, but NumPY arrays provide much more efficient ways of storage and data operations as the size of the array grows. The NumPY arrays creates the core of nearly whole ecosystem of the data science tools in Python. So, irrespective of the field of your interest in the data science, NumPY will always be a valuable asset for learning. You have already installed Anaconda Stack, the NumPY library would have been already installed. If not, you can install it based on your operating system and the process is very much straightforward. Let us start our discussion with the NumPY arrays and compare them with normal Python arrays. NumPY array are the backbone of numerical computing in Python. They are multidimensional, homogeneous data structures that store elements of the same data type. This uniformity in data type allows NumPY arrays to perform operations efficiently across large datasets. On the other hand, normal Python arrays, also known as lists, can store elements of different data types. While they offer flexibility, they are not optimized for numerical computations involving large datasets. Let's illustrate this with a simple example. Suppose we want to perform element-wise addition on two arrays or lists. Here, we define two Python lists, Python_list1 and Python_list2 containing integers. Then we use list comprehension along with the zip function to add corresponding elements of Python_list1 and Python_list2. The result is stored in Python result, and we print it. For normal Python lists addition, the result is 6, 8, 10, 12, because 1 plus 5 is equal to 6, 2 plus 6 is equal to 8, 3 plus 7 is equal to 10, and 4 plus 8 is equal to 12. Next, we import NumPy as NP and create two NumPy arrays NumPy_array1 and NumPy_array2 using np.array function. We directly add the two NumPy arrays using the plus operator. The result is stored in NumPy result, and we print it. For NumPy array addition, the result is sum of each corresponding elements, meaning each element is added element-wise, similar to the Python list addition but presented in a NumPy array format. Next, we will discuss about creating arrays from scratch with NumPy. So, creating arrays from scratch using NumPy can be very useful, especially when dealing with larger datasets. Let's go through several examples to see how we can do this. Example 1. Creating an array filled with zeros. Here, we create a NumPy array of length 10 filled with zeros and specify the data type as integer. Example 2. Creating a 3 by 5 array filled with ones. This line creates a 3 by 5 NumPy array filled with ones, and we specify the data type as float. Example 3. Creating a 3 by 5 array filled with a specific value. Here, we create a 3 by 5 NumPy array filled with the value 3.14. Example 4. Creating an array with a linear sequence. This line creates an array starting from 0, ending at 20, exclusive, with a step size of 2. It's similar to the range function in Python. Example 5. Creating an array with evenly spaced values. This creates an array of 5 values evenly spaced between 0 and 1. Example 6. Creating a random array. Here, we generate a 3 by 3 array of random values between 0 and 1. Example 7. Creating a normally distributed random array. This line creates a 3 by 3 array of random values with a mean of 0 and a standard deviation of 1, following a normal distribution. Example 8. Creating an identity matrix. This creates a 3 by 3 identity matrix where diagonal elements are 1 and others are 0. So, these examples showcase the versatility of NumPY in creating arrays of different types and shapes, which is essential for numerical computations and data manipulation in Python. Now we will discuss about the introduction to data manipulation using NumPY arrays. So, when it comes to manipulating data in Python, NumPY arrays take center stage. They are the backbone of data manipulation, and even newer tools like pandas are built upon the foundation of NumPY arrays. In this section, we will discuss about various examples of using NumPY array manipulation. These techniques will help you access data and subarrays, split and reshape arrays, and join them together. While these operations might seem a bit technical at first, they are the fundamental building blocks that support many other examples and applications discussed in this course. So, it's important to familiarize yourself with them because they form the basis for more advanced data manipulation techniques. Here are the few of key categories we'll cover in this section. The attributes of arrays. This includes understanding the size, shape, memory usage, and data types of arrays. Indexing of arrays, learning how to get and set individual elements within an array. Slicing of arrays is like working with smaller subarrays within a larger array. Reshaping of arrays, which means changing the dimensions or shape of an array. Joining and splitting arrays, is about combining multiple arrays into one and dividing a single array into multiple parts. By mastering these array manipulation techniques, you'll have a solid foundation for working with data effectively using NumPY in Python. So, let us start looking at first at the attribute of the array. To begin with, we will create 3 random arrays. A 1, 2, and 3-dimensional array. Here, we use NumPy's random number generator and set the seed to 0. Setting a seed ensures that the random numbers generated are reproducible. That means every time you run the code with the same seed value, you'll get the same random numbers. So, in this example, x1 is a one-dimensional array with 6 elements, each randomly chosen from integers between 0 and 9. x2 is a two-dimensional array with a shape of 3 and 4, meaning it has 3 rows and 4 columns, filled with random integers from 0 to 9. x3 is a three-dimensional array with a shape of 3, 4, and 5, indicating it has 3 matrices, each containing 4 rows and 5 columns, filled with random integers. Now, let's explore some key attributes of these arrays. Like number of dimensions, this tells us how many dimensions each array has. Shape. The shape attribute specifies the size of each dimension of the array. Size. This attribute indicates the total number of elements in the array. For instance, if we examine the three-dimensional array x3, we can print its ndim, shape, and size, and here is the explanation of the output. x3 ndim, this line prints the number of dimensions of the array x3, which is 3. It means that x3 is a three-dimensional array. x3 shape, the shape of x3 is printed as 3, 4, and 5. This indicates that x3 has 3 dimensions, with the first dimension having size 3, the second dimension having size 4, and the third dimension having size 5. So, it's a 3 by 4 by 5 array. x3 size, the size of the array x3 is printed as 60. This represents the total number of elements in the array, which is calculated by multiplying the sizes of all dimensions together. 3 times 4 times 5 is equal to 60. Another crucial attribute is the data type of the array. In our case, x3 has a type of int64, indicating that it stores integers. Additionally, NumPY arrays have attributes like itemSize and bytes. itemSize, this attribute specifies the size of each array element in bytes. nBytes, it denotes the total size of the array in bytes. In general, the nBytes value should equal itemSize multiplied by the size of the array. These attributes provide crucial insights into the structure and memory usage of NumPY arrays, making them indispensable for data manipulation and analysis. Now let us move to array indexing, By now we hope that you are comfortable with how you access elements in regular Python lists using indexes like using square brackets. Well, NumPy also makes it just that easy. Let us see with some examples, like single-element access in one-dimensional arrays. Let's say you have a one-dimensional array like this. To grab a specific item, you use square brackets just like in regular lists. So, x1, 0 gives you the first item, which is 5. And the x1, 4 gets you the fifth item, which is 7. You can also count from the end using negative indices. So, the x1 to 1 gives you the last item, which is 9. And the x1 to 2 gets you the second to last item, which is 7. Now, let's move to arrays with more dimensions, like this one. To access items in this multi-dimensional array, you use a comma-separated tuple of indices. So, x2, 0, and 0 gives you the element at the first row and first column, which is 3. Similarly, x2, 2, and 0 gets you the element at the third row and first column, which is 1. And in last, x2, 2, and -1 gets you the element at the third row and last column, which is 7. You can also, modifying array elements using the same indexing method, for example x2, 0, 0 is equal to 12 modifies the element at the first row and first column to be 12. But we have to keep in mind that, there is a crucial difference between the regular Python lists and NumPy arrays. The NumPy arrays have a fixed data type. Which means that if you try to put a different type of value in, like a floating point number into an integer array, NumPy will silently change it to fit the array's type. Let us now dive into array slicing in NumPy, which is a handy way to access specific parts of your arrays easily. The syntax for same is xstart, stop, and step. In upcoming examples, we will see accessing elements from both one-dimensional and multi-dimensional arrays. Starting with one-dimensional subarrays, imagine you have a one-dimensional array like this. Now, using slicing, you can grab different parts of this array, for example. x5 will give you the first 5 elements. x5 will give you elements from index 5 to the end. x4:7 will give you elements from index 4 to 6. x2 will give you every other element. x-1 will reverse the array. Let's now move on to multidimensional arrays. Suppose you have a 2D array x2 like this, so, as usual with slicing, you can slice along rows and columns, for example. x2, 2, 3, will give you the first 2 rows and first 3 columns. x2, 3, 2, will give you all rows and every other column. x2::-1:-1 will reverse both rows and columns. So, slicing in NumPy lets you extract specific parts of your arrays efficiently without creating unnecessary copies, which is great for working with large datasets. To access specific rows or columns of an array in NumPy, you can combine indexing and slicing techniques together. For example, let's consider a 2D array x2. You can access the first column of x2 using x2:0. Similarly, to get the first row of x2, using x2:0, smiley face. For row access specifically, you can omit the empty slice for a more concise syntax like this. Next, we will discuss about reshaping arrays. It is a handy operation in NumPy, and you can do it using the reshape method. Let's break it down and understand how it works. So first we create a one-dimensional array named grid. Suppose now you want to arrange numbers in array into a 3x3 grid. You can achieve this with the reshape method like this. Here, we start with an array containing numbers from 1 to 9 using np.arrange, 1, 10, and then we reshape it into a 3x3 grid. Let's dive into array concatenation and splitting in NumPy. To begin with, we will look into the array concatenation, which is like merging or combining arrays into a single, larger array. Imagine you have 2 arrays and you want to join them into one big array. NumPy provides several ways to do this. First, let's look at np.concatenate method. It takes a tuple or list of arrays as input and joins them together. For instance, the combined array will now hold the result of merge of X and Y array. You can even concatenate more than two arrays at once. When dealing with multidimensional arrays, you can concatenate along different axes. For example, the concatenated rows will be a 3 by 4 array, and the concatenated columns will be a 4 by 3 array. Like in this example. If you prefer more explicit stacking, you can use np.vstack for vertical stack and np.hstack for horizontal stack. For instance, first, we have two NumPY arrays. Now, let's see what happens when we vertically stack X on top of grid using np.vstack. The np.vstack function stacks arrays vertically, meaning it puts one array above the other. So, X, which is 1, 2, and 3, will be stacked on top of grid. Here's the result you'd see printed. As you can see, X becomes the first row of the new array, followed by the rows from grid. Next, let's look at horizontal stacking using np.hstack. In this result, each row in grid is combined with the corresponding row from Y horizontally, extending the number of columns in the final array. These stacking operations are handy for combining arrays in different ways, whether you need to stack them vertically or horizontally based on your data arrangement needs. Now, let us move on to array splitting, which is like breaking a large array into smaller parts. NumPy provides np.split, np.hsplit for horizontal split, and np.vsplit for vertical split for this purpose. For instance, you can split an array into multiple subarrays at specified indices using np-split. Here, X is split into 3 parts based on the indices 3 and 5, resulting in x1 equals 1, 2, 3, x2 equals 99, 99, and x3 equals 3, 2, 1. Similarly, you can split multidimensional arrays using np.vsplit and np.hsplit. For example, the upper and lower arrays are split vertically, and left and right arrays are split horizontally based on the specified indices. These operations are incredibly useful for organizing and manipulating data in various ways, making NumPy a powerful tool for array handling and analysis. Next, we will discuss about computation on NumPy arrays called as universal functions also. Before we proceed, it's worth to note that, when you work with NumPy arrays, you might notice that some operations are lightning fast while others can be a bit sluggish. The secret to speeding things up lies in using vectorized operations, which are like supercharged tools for handling arrays. These operations are typically carried out using NumPy's universal functions, often abbreviated as ufuncs. Imagine you have a bunch of calculations to do on each element of an array. Doing them one by one can be slow and tedious. That's where ufuncs swoop in to save the day. They let you perform repeated calculations on array elements super efficiently. Think of ufuncs as your trusty helpers that turbocharge your array computations. They're like the power-ups in a video game that make your character faster and stronger. NumPy's ufuncs come with a wide range of arithmetic functions that are not just common but also incredibly handy. These functions are like your Swiss Army knife for array math, giving you tools for addition, subtraction, multiplication, division, and more, all optimized for speed and efficiency. Let's start with the basics, arithmetic operations. Using ufuncs for addition, subtraction, multiplication, and division feels just like using regular math in Python. When you run this code, you'll see that adding, subtracting, multiplying, and dividing arrays is as easy as pie. But wait, there's more. You can also do floor division, exponentiation, and modulus using ufuncs. These operations can be combined in creative ways. For example, you can negate an array, square it, and find remainders, all in one go. Behind the scenes, each of these operations is actually calling a specific function in NumPy. For instance, the plus operator is just a shortcut for the np.add function. Here's a handy table summarizing the arithmetic operators and their equivalent ufuncs in NumPy. Addition tool is like a calculator's addition button. It adds numbers together. In NumPy, we use NumPy.add to do the same thing. Subtraction, just like you'd subtract numbers on paper, this tool helps you subtract values in NumPy arrays. It's connected to NumPy.subtract. Unary negation, sometimes you want to flip the sign of a number, turning positive into negative and vice versa. This tool, represented by negative without a number next to it, does that job. In NumPy, it's linked to NumPy.negative. Multiplication, want to multiply numbers? This tool is your friend. It's associated with NumPy.multiply in NumPy. Division, when you need to divide numbers, this tool steps in. It corresponds to NumPy.divide in NumPy. Floor division 1 is like regular division, but it rounds down to the nearest whole number. So, 5 floor divide by 2 is 2, not 2.5. NumPy calls this NumPy.floor_divide. Exponentiation, need to raise a number to a power? This tool handles exponentiation, just like NumPy.power in NumPy. Modulus/remainder, ever wondered what's left over after dividing one number by another? That's what this tool tells you. In NumPy, it's connected to NumPy.mod. These ufuncs are like your trusty math helpers, always ready to crunch numbers and make your array computations easy. Now let us take example of absolute function. Imagine you have a number line, with positive numbers on the right side and negative numbers on the left. Now, absolute value is like asking, how far is this number from 0, regardless of which side it's on. In NumPy, finding the absolute value of numbers is really easy. Let's say we have an array with both positive and negative numbers. When we use the abs function in Python, it gives us the absolute value of each number in the array. NumPy makes this even simpler with its NP. Absolute or NP.abs function. You get the same result but with NumPy's efficiency. Now, what if we're dealing with complex numbers, like those with an imaginary part? NumPy has got us covered there too. When you take the absolute value of complex numbers, it gives you the magnitude or distance from the origin in the complex plane. So, whether you're working with regular numbers or complex ones, NumPy's absolute value function makes it easy to find how far each number is from 0. Let's now dive into trigonometric functions using NumPy. Imagine you're dealing with angles, like those in a circle. NumPy makes it super easy to compute trigonometric values like sine, cosine, and tangent. Let's start by creating an array of angles using NP.linspace, which gives us evenly spaced values. Now, let's compute some trigonometric functions for these angles and see what we get. When you run this code, you'll get the values for sine, cosine, and tangent for each angle. You'll notice that due to machine precision, some values that should be 0 may not hit exactly 0. NumPy also provides inverse trigonometric functions like arcsine, arccosine, and arctangent. Let's say we have an array X with values -1, 0, and 1, running this code gives us the inverse trigonometric values for each element in X. These functions are incredibly handy for dealing with angles and trigonometry in your data science work. Now let us move to exponents and logarithms, that are fundamental mathematical operations that are widely used in various scientific and computational contexts. In NumPy, these operations are efficiently handled through specialized functions known as ufuncs or universal functions. Let's break down how you can work with exponents and logarithms in NumPy. The exponentials, the np.exp function computes the exponential of each element in an array. For example, given an array x equals 1, 2, 3, the np.exp calculates the exponent value of each element. The np.exp2 function calculates 2 raised to the power of each element in the array. The np.power function allows you to compute a custom base raised to the power of each element. Moving to logarithms, the natural logarithm can be computed using np.log. You can also compute base 2 logarithms with np.log2 and base 10 logarithms with np.log10. The NumPy provides specialized functions like np.exp1 and np.log1p for improved precision when dealing with very small input values. Alright, let's now discuss into some advanced features of NumPy's universal functions. We know we have the ability to specify the output array for ufuncs. Imagine you're dealing with a large computation, and you want to directly store the results in a specific array location without creating a temporary array. You can do this using the out argument of the ufuncs. In this example, we're multiplying each element of the array x by 10 and storing the result directly in the y array. This can save memory and improve performance, especially for large arrays. Next, let's talk about aggregates. For binary ufuncs, those that operate on 2 arrays, we can compute interesting aggregates directly. For instance, if we want to reduce an array using a specific operation, we can use the reduce method of any ufuncs. The reduce method repeatedly applies the specified operation until only a single result remains, giving us the sum or product of all elements in the array. Lastly, ufuncs can compute the output of all pairs of 2 different inputs using the outer method. This is handy for tasks like creating a multiplication table in a single line of code. The outer method generates an array where each element is the product of a pair of elements from the input arrays. In this case, we get a multiplication table where each element is the product of 2 numbers from 1 to 5. These advanced features of NumPy's ufuncs can be incredibly useful for optimizing memory usage, performing efficient calculations, and simplifying complex operations. With this we will end this lecture here. We have seen some basic and some of advanced NumPy operations. In our next video, we will discover the powerful world of data science with the Pandas library. Pandas is a powerful Python library used for data manipulation and analysis. It provides data structures like data frames and series, along with tools for reading and writing data in various formats, handling missing data, and performing operations like filtering, grouping, and merging datasets efficiently. We hope that you have found this course informative. Please hit the like button and subscribe to our channel for more informative Python for data science content. Your support means a lot and motivates us to create more educational resources for you. Stay tuned for the next lecture, where we'll continue our journey through Python's data science course. Thank you for watching.